Hello everybody, it's Mr. Ray here with our next lesson in grade 12 advanced functions. Hope everyone's having a great day. We're going to start a new unit today. That unit is called rational functions. And before I get into the details of this lesson, I want to just talk about, well, what is a rational function so that when we do start working on it, you have a clear understanding of what it is and what it isn't. Okay, so I'm going to do a little bit of definition down here on this lesson note. So rational functions, I know that sounds a little bit like rational numbers, and they are related. So just a reminder what a rational number is. Now, a lot of times, instead of just calling it a rational number, we call it a fraction. So in order to give a little bit better detail of what that is, a rational number is an integer divided by another integer. It could be positive, negative. They can't be fraction over fraction. That's not a rational number, or decimal. It's got to be integer and integer. Okay. Now, obviously, there are restrictions on this rational number, because what if the denominator was 0? Well, that would create a divide by 0 issue. So it would be any rational, any integer over integer where the denominator can't equal 0. And we're going to see this issue a lot when we talk about rational functions. So how do we extend this definition to a rational function? Okay, and again, the rational part is the division. So if I was to define a rational function, f of x, I could say, again, I've got my division bar there on the numerator. I've got some kind of polynomial function. I'll just call it polynomial here. Polynomial, and that's divided by another polynomial function. And if you remember, a polynomial function can be all sorts of different categories or classifications. A polynomial could be just a constant, like a number. It could be linear, 2x plus 1. Could be quadratic, cubic, etc. So if I was, I'll do some examples here, but again, we have the same issue here. We can't, this function would not be defined if that denominator polynomial or expression was equal to 0. So we're going to have to look at that. But the other further clarification on polynomial over polynomial, and that is definitely true except for one thing: the denominator can't be a constant. The top can be, the numerator. And let's discuss why that's true. If I had, say, a polynomial, say, I don't know, 5x plus 10 over 2, well, those are both polynomials, but 5x plus 10, I could divide that by 2 and have 5x plus 10 divided by 2 would be 2.5x plus 5. Well, that's not a rational function. That's another linear function. Okay, so that's the reason why we can't have a constant on the bottom. It has to have some expression involving the variable x. Okay, but the top can be. You could have a 1 up there. You could have a -5. You could have everything. Okay, so that's the only restriction on how you create a rational function. Okay, so let's look at some examples. We're going to have a very specific example that we're going to be working with today, and that's this first one here. The first one, if f of x was a constant over a linear function. Okay, and that fits this definition up here. The denominator is a linear function, not a constant function, so that's okay. I could also have, and like I said, this is the one we're going to be looking at today, but I could also have another rational function where I have a constant on the top, which is just a number, over a quadratic. So this would be a degree 2 polynomial function. Okay, and I could keep going here. I could have a constant over cubic, constant over quartic, etc., forever. Obviously, we're not going to be looking at much beyond probably a cubic on the bottom for this course, but there is an infinite number of possibilities of ways to create a rational function. Now, I could change the constant on the top to a different type of polynomial. For example, I could have a linear on the top and on the bottom. For example, 2x plus 1 over 5x minus 7. That would be a rational function. Okay. I could also have, instead of them both being linear, I could have, let's see, I could have linear over quadratic. So once I get here and I've used up all the constants, I could have linear over quadratic. I could also have quadratic over linear. So I don't have to have a higher degree on the bottom. I could have the higher degree on the top as well. I could have a cubic over linear. I could have a cubic over quadratic. The sky's the limit there. Okay, so lots of others. Now, when we look at this unit, we'll have a fairly defined, we'll be looking at, well, at least these ones here, plus bring in a couple of cubics as well. Okay, so we talked about this first example here, where you've got constant over a linear expression, and that's what we're working with today. So this is, a reciprocal of a linear function. You could think of this as, well, the linear function could be anything, right? It could be, f of x equals. Now, I'll use normally we would use the definition mx plus b as our linear. For some reason, the textbook has liked to switch this up, just to confuse us a bit, but really k and c are just variables like m and b are. So the official definition for this lesson is for a reciprocal of a linear function. Well, there's the linear function, kx minus c. That could be a plus c as well, but for reasons we'll see down here, they used a minus c. I'm not a big fan of using this, but that's just for your reference if you want it. Okay, so we got our linear function on the bottom and we flipped it. So normally a linear function would be like kx minus c over 1, and if we take the reciprocal, the 1 now comes on the top, and this is a reciprocal of a linear function. So this definition here could define any reciprocal of a linear function, which is a rational function where you have a constant on the top, which in our case for this lesson will be a 1, and the linear is just any linear function on the bottom. Okay, so now we're gonna see some strange things going on when we sketch any of these rational functions. We're going to be seeing things called asymptotes, and some of you have seen this before, some of you haven't. An asymptote could be a vertical line, call that a vertical asymptote, or it could be a horizontal line, which is a horizontal asymptote. These lines, any asymptote, basically the definition for now will be the graph of the function, the rational function, will never cross that asymptote. Okay, and today's lesson, we're going to be actually learning techniques on how to find the different asymptotes and how to use those to come up with other information that we can use to sketch the graph. So that's really what today's lesson is all about. So lots of new techniques, lots of new definitions. We'll be sketching, I believe, 3 different graphs using the techniques. Maybe it's 2, we'll see. Now, you don't have to really get too much into this. I'll be explaining this when we do our examples, but if you use this definition of your rational function that we're working with today, you can see the difficulty, and we talked about this. This function would not be defined if that denominator was equal to 0. So if whatever that value of x is that makes the denominator 0, that's where we're going to have a vertical asymptote. So if we want to find the vertical asymptote, and the vertical asymptote really is just values of x where the function doesn't exist. It can't be that value. So what we do is we set the denominator equal to 0 and solve for x. So in this example with kx minus c on the bottom, the vertical asymptote's equation would be x equals c over k. Now, anytime you define a vertical asymptote, a lot of students will forget that this is a line, so you have to use the equation that starts with x equals. That defines a vertical line. The vertical asymptote is not c over k. The vertical asymptote is x equals c over k because it's lots of different points, not just one value. Okay, so there we go. There's the definition of the asymptote, and that's where the domain is not defined. Okay, now we're going to actually, when we graph a vertical asymptote and a horizontal asymptote, we're gonna put like a dotted line or a dashed line to show where those asymptotes are. Those aren't part of the graph of the function, but it's very useful in looking at the behavior and what the actual graph looks like. Okay, now this has a little asterisk here. This is true for the reciprocal linear function and for some other ones we're going to look at, that the horizontal asymptote will have the equation y equals 0 for today's lesson and the next lesson, but this will not always be true, and we'll look into the horizontal asymptote, how you determine what it is in the future lessons. Okay, so for now, again, the horizontal asymptote is always y equals 0, but that's going to change, so don't get too set in that belief. Okay, I'm going to skip this for now. This relates back to the k that's in your function here, whether or not the slope of the line is increasing or decreasing. I'd rather just look at how you determine that from your information that we're gathering. Okay, so let's get into some examples of our first type of rational function, which is a reciprocal of a linear function. You can see we're looking at this function now, f of x equals 1 over 2x minus 1. You can see that the denominator definitely is a linear function, linear equation, and we have a 1 on the top. That tells us a linear reciprocal of a linear function. So this is a rational function, our first family of rational functions. Okay, now I didn't really leave a lot of room here for the amount of work that we're going to do, so it might seem a little bit squished. I'm actually going to do the graph over here, which is part D, but for this first example, I really wanted to show you how we come up with the values instead of just using what you'll probably do in your homework and in future lessons. You probably won't put all this detail that we're going to show here, but I think it's important so that you can learn how you actually do the process and how you what you have to do in your head, which you may not have to write out after you've done this a few times. And I'll tell you what I expect to see, but it's a little bit overkill just to help describe what we're doing. So we're going to be doing a few things here. We're going to state the domain. What are the possible values of x? Describe the behavior of the function near the vertical asymptote. So we have to figure out what the vertical asymptote is, and we get that from the domain. And then we do something called describe the end behavior. Then we're going to sketch the graph and then state the range. Okay, so the first thing we're going to look at is the domain. Okay, and a reminder, what is the domain? The domain is all values of x. Now the only thing we have to worry about is except, so it's going to be all values of x except where the denominator equals 0. Okay, so and this will be a step that you don't have to do every time, but if I want to find out what that value of x is, I just set the denominator equal to 0. So in this case, 2x plus 1. Sorry, minus 1. 2x minus 1 equals 0. And I'm not going to go through every step of solving a linear equation, but it's 2x equals 1, so x equals 1/2. So in terms of this question, what's the domain? Well, it's going to be all values of x except for x equals 1/2. Now, we're going to use this now that we found the value of x that's not part of the domain in this case. That's where our vertical asymptote is. So I know it didn't ask directly to state that, but you get your vertical asymptote from knowing the restrictions on the domain. So you have a vertical asymptote, and I'm going to use the short form VA instead of writing it out, and I'm going to use HA for horizontal asymptote. So please get used to that. Should save a little bit of writing. So I have a vertical asymptote at x equals 1/2. Okay, and we're going to definitely be using that on our next step. Now, in terms of actually doing what they asked, state the domain. Let's do that now. So the domain is x is an element of the real numbers, except x cannot be 1/2. And you could put 0.5 here as well, which I think I will later on. Now you have to be careful here, because here I've got x equals 1/2. Here I've got x is not equal to 1/2. So basically the vertical asymptote is where this line exists. So it's x equals 1/2. That's the vertical line where basically the function cannot cross. If I'm talking about the domain, I'm eliminating that value from possible values of x. So that's why that's not equal to, and that's why that's equal to. So make sure you understand when to use equal and not equal. Okay, part B says describe the behavior of the function near the vertical asymptote. Okay, so this is something brand new. Now that we've defined, so what we do, let me write this out, which will be something you don't have to do every time. You will write out VA behavior. So you don't have to write this part. What this is, we look at both sides of all the vertical asymptotes. And what we're looking here is, if you're to imagine, I'll do maybe just do a sketch over here. If you had a vertical asymptote here, okay, this is not applying to this question, but if you had a vertical asymptote here, you're saying, what the vertical asymptote behavior is saying is what happens as our function comes closer and closer to the vertical asymptote from the left side and from the right side. And we know it can't cross, so what's going to happen? Well, it's either going to veer off to the positive side, or it's going to veer off to the negative side. So the way we define that behavior is we say x. So for example, maybe coming from this side, it goes up, and maybe from this side it goes down. We're going to figure that out. But there's only two options that can happen with vertical asymptote behavior. You can basically say as x approaches the vertical asymptote from the left side, in this case, the y value is approaching positive infinity. It's never going to cross that line, but it's going to get closer and closer. And in this case, as x approaches the vertical asymptote from the right side, the positive side, you can see the value of y is going to approach negative infinity. So we know it's always going to be positive or negative infinity. negative infinity or positive infinity. And that's another thing I wanted to bring up here. Out of habit, I always put positive infinity and obviously negative infinity. You don't really have to put the positive. If it just says infinity, it's assumed to be positive infinity. I just like to do it because it's complete. I always know exactly which one I'm talking about. It also makes it quite clear. Sometimes a negative sign doesn't really show up. So you have that option. But if you prefer not to put positive infinity, you can just put infinity and I'll know what you mean. Okay, so this is the way we do this part. So vertical asymptote. Now it says here some both sides of all vertical asymptotes. Well, in examples we do today for this reciprocal of a linear function, we're only going to have one vertical asymptote. But as we add to the different families of rational functions, you could have 2, 3, and more vertical asymptotes. So you have to do this for each of the vertical asymptotes. So that's why I said of all vertical asymptotes. In this case, we just have one. So I'm going to state which vertical asymptote I'm talking about. And at this point, I'm going to change it to 0.5. Because it's really 1/2, but I like working with decimals if I can. So I'm going to have two statements for this vertical asymptote. The first one will say as, and I want you to use this exact terminology, as x approaches the vertical asymptote.
Sorry, could you say that again? I'm having trouble hearing you.
Okay. So for this one, we want to say as x is approaching the vertical asymptote from the left side or the negative side. So I'm going to put a little negative sign up here, and that means coming from the left or coming from the negative side. Okay. The other side, which I'll just show you the form here, will be the same, except this one is going to be a positive sign. So this says as x approaches 0.5 from the positive side. Okay. Now, this is the part you don't have to include in your statement, but the way I do these, and I think you'll appreciate the way this works, I'm going to come up with a value that's close to 0.5, but on the negative side. So I always use a difference of 0.01. So I'm basically going to plug in a value of x of equal to, so this is on the negative side, so that's going to be 0.01 less than that, so that's 0.49. Okay, you don't have to do this each time, but this is the way you would do it in your head. Okay, so I should put the word use. You don't have to. This is a fairly arbitrary value that I always use. Now for the second branch here, for the behavior from the right side, the value will be 0.01 higher than the 0.5, so that would be I'm going to use x equals 0.51. So you can see this is an x value that's to the left or the negative side of this vertical asymptote, and the 0.5 is slightly higher than the vertical asymptote, so it's on the right side or the positive side. Okay. If I try to plug in 0.5, I'm going to get something undefined. Okay, because well, you're going to get 0 on the denominator. So let's see what happens. So on the first branch, on the negative branch, the left side, what we're looking at is what's happening to y. So y will always be approaching, and I've already said it's either going to be, the answer to this is either positive or negative infinity, but let's just see how we get that. So if I plug in the 0.49 into the function for x, I'm going to have 1 over 2 times 0.49 minus 1. Okay. Now, it's not so much the value of this that we're looking for, it's going to be the sign, because we know it's either going to be positive or negative infinity, but let's just see why that's true. So if I was to actually evaluate that, well, I'm going to get 1 on the top, and on the bottom I get 0.98 minus 1. It's actually negative 0.02. all I'm going to put here is it's a small negative number. And that will always be true no matter what value you put in here. So a small negative. And if I can see that the smaller I make this, the larger the overall number is, but it's always going to be negative because the number on the bottom is negative, the number on the top is positive. So this is going to result in the overall end behavior that as x approaches 0.5 from the negative side, y will be approaching, and again, you could fill this in every time. You know it's positive or negative. In this case, since we know this number is negative, well, it's approaching negative infinity. And if we do the same thing for the right branch on the positive side, if we do the same thing, this time we use 0.51. 2 times 0.51 minus 1. Well, this time you notice I'm going to get 1.02 minus 1. So this time I have 1 over a small positive number. And that's going to you know, approach positive infinity this time. Okay, so that's what we mean by the vertical asymptote behavior. What's happening to the graph on both sides of each of the vertical asymptotes? So we now know. Okay, we're going to use this when we do our graph. Now we're going to look at describe, the part C is describe the end behavior. So I'll write that out. It's important that you communicate when you do this what exactly you're evaluating or trying to determine. Try to keep your answer very organized like this is. Okay, so the end behavior, if I was to look at this graph again, I'm basically asking, as x gets really, really big, what's happening to the value of y? Okay, and we already know we've been told that there's going to be a horizontal asymptote at y equals 0, which is the x-axis. Okay, so all we're trying to determine here is as we get really, really big for x, as x gets bigger and bigger, is the graph coming towards the x-axis, y equals 0, from the bottom or from the top? So is it a very small positive value, a very small negative value? And again, and we also do that from the left side. As x gets really, really negative, we know that y is approaching 0 because that's where the asymptote is. But is it coming from the top or from the bottom? Is it positive, coming from the positive side or the negative? So it's what we're doing here is very similar to vertical asymptote, but we do it in a slightly different way. So you could also call the end behavior the horizontal asymptote behavior because it's related to the horizontal asymptote. So what we're trying to determine here is what happens as x approaches negative infinity and as x approaches positive infinity. What's happening to y? And we know it's going to be, we already know it's going to be approaching 0, but we want to know from what side. Okay? So this time, instead of looking at a number really, really close to the vertical asymptote, we're just going to, first of all, to simulate as x approaches negative infinity, as it goes further and further to the left, I'm just going to pick a fairly large negative value. So I'm going to use to simulate as x approaches negative infinity. I'm just going to say, well, what is the value of the function at x equals negative 100? So again, this is an arbitrary number that I like to use. That's a pretty large negative number, and you can get your answer fairly quickly. Negative 10, negative 20 may not be as large as you need, but I think negative 1,000,000 would be overkill. So I like to use this number, and we're also going to do the other side as x approaches positive infinity. As x gets bigger and bigger, I'm going to use as x equals positive 100. Okay, so let's look at the top one as x approaches. Basically, if you plug in x equals negative 100, what is happening to the function? So all I'm going to do here is I'm going to plug in negative 100 where I see an x. So that's 1 over 2 times negative 100 minus 1. And that's going to be equal to, if I actually do the math, like negative 200 yeah, so that's negative 201. So even looking at this, okay, we know it's approaching 0, and this is really, really close to 0. But our real intent is the line approach, is it coming from below or above? And you can see here, this is a really small negative value. So the way we put this in, the way we define this, as x approaches negative infinity, y approaches 0, because that's where the horizontal asymptote is, and we know it's approaching from the negative side or the left side. So I'm going to put a little negative sign there, and that really means it's coming from below. Okay, try to squeeze that in. And if we do, so we know out on this end of the graph, this obviously doesn't match with what we've got. As we get further and further to the left, our graph is coming up from below and approaching 0. So what happens when we plug in positive 100? So you're going to see this is 1 over 2 times 100 minus 1. That's equal to 200, 1 over 199. And again, you can see that's a really small number that's close to 0, but this time it's positive. And that's the important part of this, is we know that y will be a very small positive number. That tells us that y will be approaching from above, from the top of y equals 0. Okay. Now the graph I'm going to do over here, squeeze it in. Again, this is a sketch, right? It's not. We're going to be gaining a little more information on more detail to do a better job on our graph in the next few lessons, and actually in the next example as well. So here is our graph. Now, so the first thing I'm going to do is I'm going to put where our vertical asymptote is. So the vertical asymptote is x equals 0.5. So I'm going to put a value there, x equals 0.5. And this is a vertical asymptote, so this is where I do my dashed or dotted line. And this is useful not just so that I know that you know where the vertical asymptote is. When you're actually doing a graph, you'll say, oh, I can't, this is kind of a stop sign here, you cannot cross that line. Okay, so when you do your sketch, it's very helpful. Okay, now what we're going to do is sketch the vertical asymptote behavior. And the way we do this, obviously I don't know what the graph looks like, but I'm going to put little indicators on the left side and the right side of my vertical asymptote. So if I go back here, I go if x is approaching from the left side of 0.5, y is approaching negative infinity. So that tells me, as I'm coming from the left side, it's either going to veer off to positive infinity or negative infinity. Well, in this case, it goes to negative. So what I do there is very, very close and far down here. I'm going to put a little direction arrow, make it nice and visible. And this basically, I'm using this statement here. As x approaches 0.5 from the negative side, y is approaching negative infinity. And if I do the same thing, as x approaches 0.5 from the right side, y is approaching positive infinity. So from the right side, my graph is going to go up this way. Okay, we're gonna connect. We're gonna create something after we've done the next part. So the next part, again, it applies to the horizontal asymptote. Okay, and we know the horizontal asymptote for the first two lessons at least. That's going to be y equals 0. Maybe I'll put that here. So at y equals 0, that's this horizontal line here. It's a little hard to do a dashed line because that's the x-axis. So I just do it slightly above, and you can see there's my horizontal asymptote, there's my vertical asymptote, and I can't cross either one of those two lines. Okay, so what are we going to use from this? We're going to use the end behavior. So as x gets more and more negative, y approaches 0 from below. So as I'm coming this way, y is coming from below. So I'm going to put a little arrow below the horizontal asymptote on the negative side. And if I read the second part here, as x approaches positive infinity, as it goes more and more to the right, y approaches 0 from above. Okay, so in this case, it's coming from above. So I'm going to do my arrow here. And now you can see I've got 4 arrows, one going left, one going right, one going up, one going down. And now the idea is just to connect the lines. Now, if we had a bit more information, we could kind of determine what these curves are going to look like, and you're going to get pretty good at that. For the time being, you're going to see, and you can verify this with Desmos, the line always kind of veers kind of towards here and then cuts off. So I can see here this arrow and this arrow have to connect because they can't go outside of this quadrant, if I want to call it that. So I'm just going to draw a fairly symmetrical line like that. And you can see I haven't crossed any of the asymptotes, so that's good. Now I have a similar set here. Now there's the y-axis. I can definitely cross that. That's not an asymptote. So something like that. Now again, there's a fair bit of guesswork as to what's going on between here and here, but you get the general idea of what the graph looks like. You can see. Now, what we're going to do on the next examples, we're going to gather a bit more information. We're going to try to find x and y intercepts. So obviously, if I knew the y-intercept here, I could get a more accurate information on where that point is. Okay, so we're going to add information to make it a little more useful. Now, the last part we haven't done is state the range. And you can kind of see why we did the graph first, because with just this information, you can't really determine, well, what is the range. Now, what we can't, so the range, if you remember, I'm not going to write it down here. It's the possible values of y. Now, if I could basically, I know that this line here is going, all the way from the, sorry, you can't see that, all the way from the top. So y goes from basically positive infinity, it comes down here and then it veers off and it comes really close to 0 and then it comes back down here. So that's a really small negative value for y, but not 0, and then it continues down here to negative infinity. So there is a break right here at the horizontal asymptote where the y is not defined, and that's for y equals 0. So I'm going to put this right here. Y is an element of the real numbers, and y cannot be equal to 0. So that really defines, where the horizontal asymptote is. Okay, that's a break in the range. Okay, so I know that took a while, but this is really important skills that you're going to need for the rest of the unit. Okay, so let's look at example 2 here. Now we're not going to do everything we did on the previous example, just going to find the x and y intercepts. So this is, like I said, an additional piece of information that could be useful for our sketch. So a reminder, people always forget, how do you find the x and y intercepts from an equation? The x-intercept is always where y equals 0, and the y-intercept is always where x equals 0. So if you remember that, it becomes fairly easy to do this. So we're basically going to set y equal to 0 to find the x-intercepts. Now the y here is the g of x. right? So we're going to set that to 0. 0 equals 2 over x plus 5. Now, anytime you have 0 equals any kind of fraction or rational expression, basically you don't really care what's on the bottom. What you're trying to do is make the numerator of this 0. So I could basically change this equation to x equals 2. And you can quickly see that, well, that's never going to be possible. I could never make this numerator 0 because it's always 2. There would have to be a variable up there for me to do that. So 0 equals 2, well, that's a false statement. So 0 can't equal 2. So I'll just say can't happen. So therefore, if you can't figure out the x value that makes this true, which it can't be true, there is no x-intercept. Okay, and that does happen. So now for the y-intercept, this is always a little bit easier because now we're setting x equals 0. So remember, g of x is y. So this time I go y equals 2 over, and this time I set x equal to 0, so 0 plus 5. So that is a number, 2/5, or 0.4. So 0.4 is the y-intercept. And again, I feel quite confident changing 2/5 to 0.4 because it's exactly the same. So people always ask, can I always change this to a decimal? Well, if this was 1/3 or 2/3, obviously you're going to get a run-on decimal that you're going to have to round. So I don't want you to do that. So if you can have a decimal equivalent of a fraction, go for it. But if you have to round, don't do it. Leave it as if it was 1/3, leave it as 1/3. Okay, so that's how we can find x and y intercepts for any rational function. Sometimes they don't exist, but that is still useful. So our last example here. There's probably easier ways of doing this, but this is a good chance for us to reconfirm our skills. So this is saying describe the intervals where the slope is increasing and the intervals where it is decreasing in the two branches of the rational function h of x equals -1 over 5x minus 2. So I have no idea what this graph looks like. So let's sketch the graph. To get our answer. Once we see what the graph looks like, we can just make our deduction visually. Okay, so I'm going to go through the exact same process we did in examples 1 and 2. So the first thing I'm going to do, I'm going to kind of trim this down a bit into something a little more manageable. So the first thing we do is we get the vertical asymptote. And again, if I do my work over here, I would say to get that, we go 5x minus 2. When is that equal to 0? So you solve for x, you end up getting x equals 2/5, or 0.4, which is exactly the same. Now let's do the vertical asymptote behavior. So the first one, well, there's only one vertical asymptote, obviously. So as x approaches 0.4 from the negative side, and as x approaches 0.4 from the positive side, again, now that I know that vertical asymptote always has two possible answers here, it's always going to be either positive or negative infinity. So I'm going to put that there for now, and I'm just going to add a positive or a negative sign in front. Let's see the calculation here. So again, for this one, to get our answer here, so I'm going to plug in something that's 0.01 less than 0.4, and that's coming from the left side, so it's going to be less than 0.4. So I'm going to put, and I'm actually going to put the negative sign from here on the top just to make it easier to work with. So negative 1 over 5 times 0.39 and minus 2. Now, the only important thing here is the sign of this calculation. So we already know the top is negative, so I'm going to put negative on the top. We just have to figure out if this is positive or negative. This does work out to be negative because this is going to be less than 2. So something less than 2 minus 2 will be negative. So I have a negative over negative, which is positive. So that tells me that the behavior to the left approaches positive infinity. Now to do this branch here, as x approaches 0.4 from the positive side, I'm going to use my test value of 0.41 because that's 0.01 higher than that. So this time it's negative 1 over 5 times 0.41 minus 2. And again, you don't have to show me this, but you do have to do this in your head or on a calculator to get, to get the overall sign here. So this time we're going to have a negative always because that's negative 1. This time this number here is going to be higher than 2. So say 2.05, I think it is. 2.05 minus 2, that's going to be positive. So this time we have a negative over positive, which tells us overall that's going to be negative. So as x approaches from the right of the vertical asymptote, it's going to go towards negative infinity. So all right, and we're going to use that in our sketch. Now we do the end behavior. So I'll put I guess I can put my vertical asymptote here just to make it totally clear, and my horizontal asymptote here, which we know will be y equals 0 because we were told that. Okay, so this time we're saying as x approaches negative infinity and as x approaches positive infinity, what's happening to y? Well, we know y will be approaching 0 because that's where the horizontal asymptote is. But again, we're just looking, is it coming from the top or the bottom? So we're going to add a plus or a minus sign on each of these, and the way we determine that is by a little calculation again. So this time, again, I'm going to use my function from here. This time from the negative side, remember we plugged in negative 100. So 5 times negative 100 minus 2. And again, you could do the sign thing here, because definitely, yeah, let's do that. So I have a negative. Actually, no, let's do the actual value because you're going to have to do this in a couple of lessons from now. So I'm going to have a negative 1 on the top. On the bottom, I have negative 500 minus 2, so negative 502. Okay, so you can see that that's a very small number, so it's very close to 0, and the overall sign is positive, so it's going to be approaching 0 from the positive side because we have 2 negatives. So I'm going to put my plus sign there. It's approaching from the positive or the top side of the horizontal asymptote. If I do the same thing this time, I'm going to plug in 100 for x. So this time you're going to see negative 1 over, that'll be 500 minus 2, 498. So again, really small number, very close to 0, but it's going to be a negative number. So that means it's approaching 0 from the negative side. Okay. Now the last thing we're going to do is what we did in example 2, and that's what are the x-intercept and the y-intercept. So again, x-intercept is where y equals 0, x-intercept is where x equals 0. So again, you're going to see this for most of these questions for this lesson. When I plug in 0 here, I get the same issue as I had before. 0 equals -1 over 5x minus 2. Doesn't really matter what x is because I can never make the top 0 because 0 does not equal -1. So therefore no x-intercept. And then for the y-intercept, y will be, I'm plugging in x equals 0, so -1 over 5 times 0 minus 2. That's equal to, it's going to be -1 over -2, which is 1/2. So the y-intercept is equal to 0.5. Okay, so we've got all our information, so I'm going to do a sketch. Okay, so the first thing I'm going to do is put where my asymptotes are. So I know I have a vertical asymptote at 0.4. Scale doesn't really matter too much for this. So there's my vertical asymptote. I also know that I've got a horizontal asymptote at y equals 0. Okay, and now I'm going to put my behavior in. I know that as x approaches the asymptote from the left side, it goes towards positive infinity. That's our statement there. And as x approaches from the positive side of the asymptote, the right side, we're approaching negative infinity. So as I'm coming towards the asymptote here, it's going down. Okay, so make my arrows nice and bold. Okay, and then for the end behavior, the horizontal asymptote behavior, I know that as x approaches negative infinity, y is coming from the top. So I have my arrow on the top for that one, and as I'm approaching negative infinity, y is coming from the bottom. So very similar to what we did in the first example. Now the only thing we're going to add are the x and y-intercept. Well, there was no x-intercept, and that should make sense because the x-axis is actually where the horizontal asymptote is, so it should not cross there. So that makes sense. The y-intercept is 0.5. So I'm actually going to put that in as a point. You can see how that kind of tells me a little bit more information for my sketch. So I can make my graph a little bit more accurate than it would have been. And I'm going to try to join these so it looks sort of symmetrical to the other side that I've already drawn. So maybe I'll make it a little bit closer to here. Looks like that. Okay. So there's our sketch of h of x. Now we go back to our question, which seems like a lifetime ago. Describe the intervals where the slope is increasing, intervals for where it's decreasing. So h of x is increasing. Now what I'm looking for here is where is the graph going up as we go left to right. So if I look as I'm coming along here, you can see increasing, 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 break, increasing, increasing, increasing forever. So it's always increasing except for at the vertical asymptote. So I can say, I'll do this in two forms. I can use interval notation. I think most of you prefer that. So from negative infinity to 0.4, not including. So that's the kind of the left branch. And then I pick it up again at 0.4 to positive infinity. Or I could use the set notation. X is an element of R. X cannot equal 0.4. Now, at the other end, is this function ever going down? No. The only time it broke here, that it wasn't increasing, was at the asymptote. So I'm just going to say h of x is never decreasing. Okay, so that's, and you can see we just used our visual perception of what this function looks like to determine, well, where is it increasing, where is it decreasing. We didn't use any actual algebraic methods to determine this other than what we got from the graph. Okay, so got some homework questions for you to work on. And our next lesson, I believe we're going to look at reciprocal quadratic functions. So basically, 1 over a quadratic function is our next family of rational functions. Okay, so hopefully that made sense, and we'll see you on the next lesson. Take care.